to the lecture on 3.2. I apologize. I had something else I had to do there. But yeah, so we were talking about the regression model for regressing fat gain to NEA, and we were interpreting the slope and the y-intercept in context. So let's go ahead and interpret the y-intercept in context. So our y-intercept of 3.505 kilograms, that tells us what our predicted fat gain would be if the non-exercise activity changed by 0. Okay, so if NEA does not change at all, our model predicts that after 8 weeks, okay, a healthy young adult would gain 3.505 kilograms in this study. So that is how you identify and interpret the slope and the intercept in context. Okay, so now what is this LSRL good for? Well, one of the things that it's good for is for prediction. So according to our model, what does our model predict about a healthy young adult who went through a study like this for 8 weeks, who increased their non-exercise activity by 400 calories? Okay, what does our model predict? Well, to answer that, you simply plug 400 into our equation for our prediction model. Okay, so the predicted fat gain is equal to 3.505 minus our slope minus 0.003444 times 400. Okay, and what do we get? We get a predicted fat gain of 2.1274 kilograms. So don't forget your units. Okay, units are very important, okay, especially in your final answer. And make sure that you state in your final answer that the predicted fat gain is 2.1274 kilograms. Not the fat gain, but the predicted fat gain. You can also use the phrase our model predicts or the model predicts. Okay, but I would just stick the word predicted right with the actual response variable. So the predicted fat gain would equal 2.1274 kilograms. Okay, extrapolation. I talked about this in the last video. Don't go outside of the range of your x's. Okay, be very careful. Okay, you don't want to go far outside because our model isn't useful for values that are far outside the range. So for example, back here, this model, this regression model is really only good from about -100 to about a little more than 700. So if an AP exam question asks you, well, what does the model predict about somebody who increases their NEA by 1200? Okay, well, 1200 is way out here. That's outside the range. Okay, that is extrapolation. So you would literally write the word extrapolation in your answer. Okay, our model is not useful for values as high as 1200. Okay, that would be considered extrapolation. That's the red flag word. That's the key word on the rubric that the AP reader is looking for, is did the test taker recognize that that was extrapolation? Okay, now we get to the residuals. And the residuals are what I referenced in section 3.1 as the error. Okay, and it's only the error in the y direction. Okay, so you learned in elementary geometry that, hey, this point is not on the line. Well, how far is this point from the line? Okay, that would be the perpendicular distance to the line, right? Well, we don't really care how far this point is in the x direction. Okay, we don't care about that. All we care about, because really what we're trying to measure is this response variable, which is on the y-axis. So all we care about is how much is our model off in the y direction, in the response variable. Okay, so the error, what is called the residual, is y minus y hat. And that is very important that you memorize the order. The order matters. It's y minus y hat, the actual minus the predicted, or the observed minus the predicted. not the other way around. Okay, the order matters, and so that means that any of these points that are above the model, above the line, are going to have positive residuals. Any points that are below the line are going to have negative residuals. Okay, well, what does that mean if an observed value has a negative residual? For example, this right here, this person, this is an actual observed value. This was one of those 16 people that, or I'm sorry, this is now body weight and backpack weight. Okay, this is a person in our study who weighed 120 pounds, whose backpack only weighed about 26 pounds. So does our model overpredict or underpredict, okay, underestimate or overestimate the backpack weight for this person who weighs 120 pounds? Well, the model is higher than this person's actual backpack weight. So in this case, our model, our LSRL model, overestimates or overpredicted the backpack weight of the person who weighs 120 pounds. The equation for residual is little e. E stands for error. Your error is equal to y minus y hat. In that order, y minus y hat. Don't switch it around. Okay, so where does the least squares regression line get the term least squares? Because if you look at all the residuals and then you square those residuals, and this is a beautiful diagram of now taking a one-dimensional distance and squaring it to give it 2 dimensions. Then if you add all these squares together, the sum of the squared residuals is minimized, okay, by the least squares regression line. Okay, so there's many other lines that you could have drawn that kind of quote unquote fit this data, but there's only one line, the least squares regression line, that minimizes the sum of the squared residuals. These are, and we're not going to derive this. The book talks a little bit about the derivation of the formula. We're not going to derive the formula for the LSRL. We're not even going to derive the formula for the slope or the y-intercept, but I am going to present these to you, okay? And here's where this becomes useful information. Sometimes on an exam question, they'll give you 2 lists of data, so it's paired data, and then they won't give you the equation for the LSRL. They won't give you A, they won't give you B. Okay, they won't give you the intercept, they won't give you the slope. But what they will give you is the 2 lists of data. Well, how are you going to get the equation by yourself? Well, they will probably also give you the X bar and the SX. If they don't give it to you, you could just do a 1-var stat of your X list to get your X bar and your SX. But probably it'll be Minitab output, and they'll probably give you the sample mean of the X's and the sample standard deviation of the X's. Likewise, in your second list, you can do a 1-var stat and get the Y bar and the SY, okay? They will also have to give you R. R is, do you remember what R is from section 1? R is correlation. And remember when I was teaching you R and how to interpret R, if R was positive, the slope of the dots went upward. If R was negative, the slope of the dots went downward. But remember I warned you, I said R is correlation, and correlation is not exactly equal to slope. So R is not the slope, but R is closely related to slope, because if you look at B equals R, they're very closely related. R is just adjusted by the ratio of SY over SX, the standard deviation of Y over the standard deviation of X. Okay, so you could simply do a 1-var stat, find X bar and SX, find Y bar and SY. They'll give you R, and you could figure out the slope. Okay, then you could use Y bar and X bar and the slope and figure out A, and there's your equation for the least squares regression line. Now, on the AP exam, they're going to use this form of the equation, y hat equals b0 plus b1x. Okay, so you just have to recognize that b0 is just a, that's your intercept, and b1 is your b, that's your slope. Okay, so they will give you this exact equation on the formula sheet, but this will say b1, okay, and this will say b0, okay, and this will say b1. Okay, so just know that that's coming on the AP exam. Okay, you can also plot your residuals against the x's. Okay, so residual plot, and I'm going to show you, or actually just watch the video on calculator functions, and I'll show you, it shows you how to get the residuals. Okay. Hey guys, so we were talking about residuals and residual plots. So here again is the scatter plot with the actual LSRL. And we can actually plot the residuals against the x variable. And that's useful for understanding visually how good or how well the model fits, the LSRL model fits the data. So how you read a residual plot like this is you're going to scan this from left to right. Okay, so look at this, like just kind of scan it from left to right. And what you want to look for is any like clear patterns. And when I say clear patterns, it will be an obvious pattern. It'll be an obvious curved shape pattern or an obvious like parabola, like an upward facing parabola or downward facing parabola. In this case, we don't really have any clear pattern. So that's a good thing. Okay. Then the other thing we want to look for is roughly, and we're not going to count, but just kind of eyeball it, and roughly half the dots above and roughly half the dots below. Okay. And so that means we have about, roughly half our positive residuals and half our negative residuals. Okay. And that is really all we're looking for in the residual plot. So the residual plot basically tells us how good the model is, how well the LSRL fits the data. Okay, so if you see a residual plot like this, that's clearly a parabola, the least squares regression line is not a good fit. It doesn't model the data very well. Likewise, if you have a strong curved pattern, the least squares regression line is not a good fit either. Okay, so here is our definition. If we use a least squares regression line to predict the values of a response variable y from an explanatory variable x, the standard deviation of the residuals is given by, you're never going to have to know that formula. You don't have to memorize that standard deviation formula. All you need to be able to do is that will tell you, like when you have Minitab output, it tells you what S is, where there's no X and there's no Y. It tells you what the standard deviation of the residuals is. Okay. Okay, so now R squared is very, very important. R squared is a coefficient, and it's specifically called the coefficient of determination. And yes, we did see R before. R by itself is the correlation coefficient or Pearson's coefficient. Okay, R tells you how strong the data is, linearly related. So it tells you the strength of the linear association between the x and the y. Now, when you square R and you get R squared tells you how good or how well the LSRL model fits. It gives you a numerical measure. So the residual plot is more of just like a quick check, like a visual, kind of a visual guide as to whether the LSRL is a good fit. R squared is a mathematical, it's more of an algebraic, numerical measurement of how strongly the LSRL fits the data. Okay. And you do not have to know SSE and SST. You do not have to know that R squared is equal to 1 minus SSE over SST. That is not critically important. What is critically important is that you're able to interpret R squared in context of any problem. Any single regression problem you have, you're always going to have to interpret R squared in context. And this is how we do that. So R squared tells us, and this is worth writing down in your notes, R squared tells us the percent of the variation in y that is accounted for by the LSRL model. Okay, so it tells us the percent of the variation in y that is accounted for by our LSRL, which regresses the y on the x. Okay, so let's say that we have an r squared, and they're either going to give you the r squared in Minitab output, or you can calculate the r squared. In this case, you can see that the r squared is given to you as 0.63. And again, this is the body weight and backpack weight study that we did. Okay. So here is our interpretation. So r squared is equal to 0.632. That tells us, and I'm reading this sentence right here, which is critically important for you to memorize, 63.2% of the variation in, now you don't just say y, you contextualize it, right? So you'd say what the y actually is. So 63.2% of the variation in backpack weight is accounted for by the linear model relating weight to body weight, or backpack weight to body weight. Okay. Another way of saying this is that 63.2% of the variation in backpack weight is accounted for by the LSRL model relating backpack weight to body weight. Okay, you also have to be able to read computer output. Now, computer output is really nice. Those problems are nice because it gives you all the information you need. You just have to be able to know where to find it. And it's not going to say A equals and B equals. It's going to use the contextualized words, and you have to find it. Okay. So here is Minitab output. Okay. And there's also jump output or JMP output. Okay. The most common is usually the Minitab output. Okay. So on the Minitab output, you're going to see these two variables. Okay. The predictor and the constant. Okay, the predictor and the predictor is going to be the constant and the NEA change. Okay, so you're going to have NEA change. They're going to have some type of words that relate in context to your actual prediction. Okay, so your constant, your coefficient of your constant, that's just your A. Okay, that's your y-intercept. So 3.5051. Okay, then your coefficient, okay, of NEA change, okay, your coefficient of x, that's the number that is, right next to x, modifying x, that is your slope. Okay, so it's negative 0.00344415. Okay, this is your SE of this slope, SE of that coefficient, your standard error of this slope. This is the standard error of the y-intercept. These are called the t-values, which are going to be really nice to use later on when we study the student's t-model, when we get to inference. And these are your p-values, okay, your probability values, which are also really important when we get to inference. Notice that the p-values are reported as 0. They're not actually 0. It's just that they're so low, they're rounded off to 0. Okay, so low p-values, you don't need to know this, but just in case you're curious, low p-values generally mean that the model, the LSRL model, is a good fit. That's another way of checking if it's a good fit. Now, here you have your S. Remember that S is just the standard deviation of the residuals. And then here is your R squared. Notice it doesn't say R squared, it just says R-SQ. Okay, 60.6, it's reported as a percentage. Okay, don't worry about the adjusted R squared. You're just going to use the R squared. Okay, well, what about R? Well, just take the square root of R squared to get your R. Okay. Okay, so could you actually write the equation from this Minitab output? Sure you could. So y hat is equal to 3.5051. Here's your y-intercept plus negative 0.00344415 times x. Okay, so here's some things to look out for. Okay, the distinction between explanatory and response variables is important in regression. Remember, in correlation, it didn't matter which one was the explanatory and which one was the response variable. But with regression, it does very much matter. Everything changes if you change those. Notice that when we change your explanatory and your response, okay, everything changes, right? Your standard deviation changes, your R squared and your R squared and your R squared adjusted, okay, did not change, but your standard deviation changes. The equation itself changes, okay? So your A and your B change, so be very careful. Okay, I remember that correlation and regression lines, they're only good for linear relationships. And also remember that correlation and least squares regression, they're not resistant at all. Okay, they're heavily influenced by outliers. And there it shows you how much the LSRL will change if you just take out one dot. Right? If you just take out one observation, okay, the slope changes, the intercept changes, things change quite dramatically. All right, so an observation is considered influential. Okay, so you have an influential point. Okay, if removing that would markedly change the result of the calculation. So points that are outliers in the x direction of a scatter plot are often influential for the least squares regression line. Okay, an outlier is an observation that lies outside the overall pattern of the other observations. Points that are outliers in the y direction, but not in the x direction of a scatter plot have large residuals. Let's think about that. So if you have an outlier in the y direction, that means that the model did not predict that value very well. Okay, so child 19, this is quite high above. This is an outlier in the y direction. Okay, so that means that the residual would be very large on this particular point. Okay. All right, other outliers may not have large residuals. So you might have outliers that don't have like huge residuals, okay? And influential points are, we're typically talking about in the x direction. And then finally, let's not call this association, but let's call this correlation. Correlation does not imply causation. That is a phrase to burn on your brain to memorize. Correlation does not imply causation. Okay, we never, when we're analyzing bivariate data and the relationship between them, even if they have a super strong correlation, we never imply that there is causation. That is outside the scope. That comes in chapter 5 when we're looking at experimental design. Here's an example of that. A serious study once found that people with 2 cars live longer than people who only own 1 car. Owning 3 cars is even better, and so on. There's a substantial positive correlation between number of cars X and length of life Y. Does the number of cars cause some people to live longer? No, there's factors outside of this X and Y that influence the Y, like generally wealth, right? People who have more cars generally are wealthier, and people who are wealthier generally can pay for better medical care. Okay, guys, that's all we have. Hope you enjoyed the videos, and we'll see you next time in class.